Welcome back, everyone. I hope you had a refreshing coffee break and enjoy connection with fellow participants. Our next speaker is someone whose story I believe will resonate deeply with many of us here today. Sanja Scepanovic is a senior research scientist at Nokia Bell Labs in Cambridge, where she works at the intersection of AI, network science, and data for social and environmental impact. Her research focuses on how artificial intelligence can help us better understand the world around us, from climate and sustainability to how data can be used to support well-being and societal progress. Before joining Bell Labs, Sanja completed her PhD at Aalto University in Finland, following her studies here in Montenegro, which makes her journey especially meaningful for today's audience from Montenegro. While she's not the only keynote speaker with Montenegrin roots, she is the only one who went through our local education system, and that's something truly special. It's a story that shows how local talent, with the right opportunities and curiosity, can grow into a global force in science and innovation. Her talk, AI for Earth Observations, explores how much machine learning can help us make sense of the planet's data, understanding patterns in the environment, and contributing to a more sustainable future. Please join me in welcoming Dr. Sanja Scepanovic with her talk, AI for Earth Observation. Sanja?
Dobro jutro. Hello, everybody. It's my pleasure to be here. As she said, I studied in the University of Montenegro, and it's always a pleasure to be back home. So I will talk to you about AI for Earth observation. And before starting, I want to see your hands. Do you know what we mean by Earth observation? Just raise your hand if you know. If you have an idea? Okay, I expected so, because it's not a very common topic. And that's why let's start first with introducing. So what we mean? Earth observation can be defined as collection, analysis, and presentation of remotely sensed data about our Earth's surface, including physical and social systems. So in other words, it's maybe Google satellite view, or it's radar imagery from satellite, or it's imagery from aircraft, and so on. And so why do we do this? Why do we need this data? Well, of course, we are going to use AI. So AI applied on this data offers many benefits. And I'm going to talk about some. It allows to monitor urban environments. Since I left Podgorica 12, 13 years ago, it has changed a lot. And I'm always thinking how interesting it would be to analyze these changes from this high aerial view. And I'll show you some examples. But also, and this is not so mainstream, this data can be used to understand public health because we can track air pollution, microclimate, we can understand greenery. What would be really meaningful, but I don't have work on this, but I think here in Montenegro, we can use this data to track wildfires. And this is actually quite a big research topic. I'd love to work on this with somebody if you're interested. So not only this can help response, so when we have very common wildfires in Montenegro as we do, this could help with response. But there is lots of research showing that this can also help predicting these wildfires. This is like the next frontier. Then with the climate change, I'm sure you are aware, we are losing our species at a really high rate. So biodiversity mapping is something that's commonly done with satellite data. And there are many other applications, but I will, in this talk, focus on the first two, where we have some recently published work. Okay, so let's start with AI for satellite data for sustainable urban planning. So there has been this very famous urban researcher, Jane Jacobs. She lived in the past century, maybe around 60s, I think. She wrote this very influential book in urban science called The Death and Life of Great American Cities. And what's been really interesting is that she was analyzing why some American cities have thrived and others that were also invested in actually declined. They became criminal hotspots. And maybe not the whole cities, but parts of cities. And she had this really influential theory which says that there are 4 factors that are going to make some city part livable or not. And she said, first of all, we need to have diversity of land use. What this means is, if we have, let's say, a residential area, it's really important that we also have some greenery and perhaps some shops and perhaps some water, but not just one type of land use. And she also said that cities need to have small block sizes. I think in Podgorica it's not a big problem, but you can imagine many large American or European cities, especially American, that were built for cars. There will be a large avenue and it's not very walkable. She argued that this is diminishing livability of cities. She also argued that we need to create environments that are going to attract people, concentration of people. And how do you do that? You need to open different amenities. You need to provide parks, maybe, maybe school, maybe like workplaces, residential, but not just one. You need to have all of those. And relatedly, she was never arguing, for example, that you only have one type of shops or one type of industry, but the most lively places are the ones where you mix. You mix something very high-tech with a small bakery shop and restaurant and so on. Okay, so this is the background. Now, this theory, proposed a long time ago, has been to some extent validated. And here I'm showing 3 studies. The first one is in Seoul, in Korea. And what they have done is they have collected for 10 years, I think. So it was a really meticulous task. They have collected lots of data about the city of Seoul. And then they explored, they were using traveling data, so as a proxy for vitality, how many people travel in each part of Seoul. And then they showed that her theory basically was applicable to Seoul. And then a more recent study has been done for Italian cities. And here they again used, for vitality, they used mobile phone density, because of course nowadays we all have phones, so mobile internet traffic was a good proxy. And then they used lots of open data. And again, the theory was holding. So then we come, and what we do? Well, we don't really need to prove the theory, but what we show is that one can use openly available satellite data to measure vitality. And why this is important? Because I do not know, probably you are aware, in Podgorica it's hard to collect all the data, even for our governments, to track all that we need. And this is the case everywhere in the world. So what we wanted to see is, can satellite data serve as a useful proxy? Okay, so that's the first project, and let me tell you what we did. Of course, out of those 4 conditions, because we wanted to use openly available satellite data, which means they are not very high resolution, we cannot see all of those. But we argued that we can see diversity of land use in satellite imagery, or see, or measure, or estimate, and block sizes. And then we focused on these Italian cities, which each has a number of districts as shown to the right. So those are the neighborhoods that you want to study. And here you see like one of those cities, and you see which areas are more lively. Now, usually centers tend to be more lively, but it's not always the case. And we collected all that data along with some ground truth data about land use mix, block sizes, and so on, as well as the mobile phone activity density as our ground truth for vitality. So this served us to now apply some deep learning methods to see if we can actually estimate vitality. So this is just one of those cities. We download the satellite image. This is openly available on Copernicus. Anyone can download. And then we crop it. This is in Earth observation, usually done into small imagelets that we can then parse with deep learning. And then we end up with around, 100, 300, 1,000, depending on the city size of those imagelets. And then we apply some feature extraction. I'll mention which methods we used. Not the most advanced. This is done some years ago. And then, I think we used convolutional neural network VGG16 and convolutional autoencoders. And then we can aggregate those imagelets for each of those districts, right? So for any area in the city, and we suddenly have a feature vector of these districts. So we have learned something from satellite imagery. And then we can apply any method to predict vitality or any of other indicators. And here are the results. They are not so great, but this is social science, and we are usually happy with anything about 0.3, 0.6. And for vitality, Here I'm showing how we performed when we were training on the 5 cities and predicting on the 6th. So it didn't work so great for Rome, adjusted square 0.3, but it worked quite well for many others, showing that basically we can capture something that's been kind of transferred in the out-of-distribution data. In other words, we can train a model that will predict how vital are the areas of different cities. And just to show you how it worked, the blue are the ground truth vitality maps, green is what we predict. So they are quite similar, but not perfect. When it didn't work, so we looked, why the model may be overestimated or underestimated. And it's kind of, now when I think about it, it's obvious. So sometimes it underestimated vitality in urban parks or near stadiums. And why? Because it has learned that usually vitality is lower in the outskirts where there is lots of greenery, but it doesn't recognize that actually a park in the middle of the city is going to be super vital. And similarly, sometimes this is specific to the Italian context. It learns that usually vitality is, as we saw from the theory, in the high density areas, right, which are central. But sometimes in Italian cities, you're going to have this high density next to the seaside, and that's not so vital. So this is another source of mistake. However, because this was just a research project and it was done with the basic satellite data, not even a high resolution, we think that it establishes a groundwork that we can use this satellite data. And this means we can use them globally, anywhere across the world, of course, with additional training and carefully adapting them. And that means that they can be used for digital twin and digital earth models. They can support urban planners, and they could even help us refine Jane Jacobs' theory, because maybe this theory is applicable to the Western cities, and perhaps there is something different about Asia or Africa or any other part of the world. So that was the first project. Oh yeah, if you want, we have a very nice visualization on socialdynamics.net/vitality or this QR code. And I will show you just a couple of, insights from the visualization. So here we are comparing, for example, just Florence and Torino. And what we color-coded is the kind of highest color in these satellite imagelets for each area. So you suddenly see that vital part of Florence is red, whereas vital part of Torino is a little bit more whitish, and this speaks to the different building materials or cultural environment or so on. And then this means that we could build vitality DNAs for the cities. So suddenly we can sort these cities based on their average vitality, and we get these nice maps. And we can really see, for example, that Palermo doesn't have the red at all because it's built with white roofs and so on. So you can see how this could be applied to other cities. Okay, so that was about using satellite data for urban planning. Now I will go to my favorite topic, but this is a very hard one, which is public health. So why do we even want to use satellite data for public health? I do not know if you ask yourself, does environment impact our health? Does it impact your own health? But for somebody like me who has lived in 7 countries after Montenegro, so I've lived in a very cold city of Helsinki, or I lived in a very distant city of San Francisco or Geneva, I have often asked, okay, water was very healthy in Mojkovac, where I come from, but it's not so healthy here. Or, I'm really freezing -20 on an average day in Helsinki in winter. How is my body reacting? And of course, there is lots of research in public health showing that environment matters. But to do this research, and especially to do it with AI, it's still hard. So public health experts, they have access to some really special, hard to get data, but usually it's very targeted to a particular condition or something like that. So just to show you, if one wanted to study asthma, one first needs obviously data on prevalence of asthma. Then one needs socio-demographic attributes, because of course a determinant of health is everything, like the economic status of people, their educational background, their race, especially in multicultural countries such as England. Of course, air quality for asthma, but even for other conditions, maybe greenery, and so it's a lot of data. And since we wanted to use also satellite, it's really lots of expertise. So basically, if one wants to do this, it's taking 70% of your time just to collect everything before you can actually get to the interesting part of studying this. So the first thing that we have done is to lay a groundwork which will help us, but also others. And we have created this data set called MedSat. This has been published at NeoRIPS 2023. And I will give you quick insights to this data is openly available. If anybody is interested, you can analyze them. This data covers 33,000 neighborhoods, small areas across whole England. And what we leveraged is that this is quite particular to England. National Health Services in that country, they release data aggregated about all the prescriptions that were prescribed to any patient. So imagine in Montenegro, if you would know at each maybe local hospital or each area, all the prescriptions, obviously anonymized, but still, that were prescribed. So this is quite rich data, and we have parsed them in some probabilistic manner to have the health outcomes. So we know, for example, how many antidepressants there were prescribed or asthma prescriptions. And then we built this data set. So we also collated census data from UK, hundreds of socio-demographic variables. For example, in each area, we know how many people work from home, or what's their economic status, how many of them are Asian, and so on. Then we also have 40 environmental indicators. Here I'm showing NO2, which is a pollutant, or we have many others. We have climate, we have greenery, and then these health outcomes that I mentioned from prescriptions. And also we have parsed satellite imagery in a very usable way for each neighborhood. So that's also something that could be used. Okay, so now I will give you some insights. So we have published this, I think, 2.5 years ago or 3 years ago. Since then, I know it's been used in maybe 12 master theses, if not more, some of which I supervise. And then also we have published some work. Before showing the work, even if one looks at this raw satellite imagery, and here we are showing in the top row areas which have high opioid prescriptions, and in the bottom areas which have low. Even just by looking, you really can see the differences. So if you pay attention, the bottom row is more zoomed in, which means those are smaller neighborhoods, whereas the upper ones are larger areas. And actually, in the outskirts, for some reason, so in the rural areas, people use more opioids. That's been known in public health. And the other is the purple color, which is higher in the upper row, which is actually satellite imagery capturing aerosols. So, there is some indication, but now I will go into actual analysis. So these are some of the publications, some which we still haven't published, many which we did. And I will first cover this one. This is the work led by Cynthia Rudin from Duke University. She's one of the leading mathematicians applying her methods on interpretable machine learning. So let me show you what they could do from this METSA dataset. Again, as you remember, we have hundreds of variables that we have collated. So the green ones are socio-demographic, the pink ones are environmental, and we even have satellite features. So what we can do is we can feed this into a machine learning method. We don't know how it works, as Razvan has shown, but it works. And specifically now in this case, I think we were using more traditional methods. So geographic weighted regression and additive models, which are applicable also to spatial data. So it was not so much maybe about the most advanced methods, but the way how we worked to interpret them was, I think, the main contribution in this work. So basically, we are predicting health outcomes from our variables, and then we are trying to understand which features the model pays the most attention to, which features are important. That might tell us what is important, for example, for antidepressants, what is protective for asthma, and so on. Okay. So I'll just show a couple of results. The paper has many results. Let's take a look at asthma. So the right plot is showing, visualizing asthma concentrations across UK. So if you think about it, what you can see is that cities tend to have a bit lower, which is the blue color, lower concentrations, and the rural areas have higher. And then To the left, we are going to look at NO2, which is a very well-known pollutant. It results, for example, from vehicles, from the emissions from vehicles, but also from other sources. And there is something interesting. When we put this in the model, all the previous public health research shows that NO2 is associated with worse health, obviously, especially asthma. But we are getting counterintuitive link. We get less. So then we had to dive deeper. But I think the image already gives us a hint as to why. Because we have less asthma prescriptions in the cities, but that's where we have the most NO2. Because cities are full of cars and full of industry. So we wanted to understand, okay, but how come? Because we are controlling for so many variables, this should not be happening. So how do we analyze this unintuitive link? Well, it happens so that from around 2019, I think, in London and in many cities in England, they have introduced ultra-low emission zones policies. This basically means that for the inner city areas, if you want to enter with the car, you have to pay some fee. And this fee is quite high, and many people simply avoid driving to these areas, which in turn means there is less vehicular emissions. And what we find is that it's exactly those areas where this policy is introduced, which have this weird link, whereas even the neighboring areas, just next to them, they don't. They have more expected link. And so our conclusion from this is that because of these policies, vehicular NO2 has been reduced, but not the rest. And this is producing counterintuitive link. In other words, it's telling us that actually these policies are really working. They are also beneficial for health. And it would be interesting to study this in other cities and countries too. Okay, so that was one. And now I will just give another example from this same paper. So anxiety prescriptions. Solar radiation, so the amount of sunny days that we get, has been one of the strongest predictors, which is maybe not so surprising, but an interesting thing is that this is not a uniformly distributed predictor. It really depends where you are in England. And there is like a clear, very interesting, clear cut between northwest of England and southeast. So what does this plot that I'm showing mean? It means that in the blue areas, more solar radiation is associated with less anxiety prescriptions. So if there is more sunny days, people are kind of feeling better. But in the middle, you have this grayed out area where there is not such a strong link. And then in the southeast, you have a counterintuitive maybe link, more sunny days, more solar radiation, people are more under anxiety prescriptions. And this is very interesting because it's showing us the effects of climate change, urban heat islands, but also maybe this part of England is a little bit more like polluted and the waters around it are hotter. In summary, the link between environment and health is not straightforward. It really depends. In some area, you might need more sun. In some area, you might prefer less. So that's another finding that we had. And I think, yes, I think I will not cover that paper anymore. But I will quickly cover one which is under review. So we still haven't published this, but I'm really excited about it. And I think then that will be all the papers. So this paper we call vitamin N, which stands for nature. So greenery, nature. And what are the benefits for health? Now, I'm pretty sure all of you know, have heard, think that more greenery is associated with better health. That's kind of a standard, or like more parks or more green environment. That's kind of a standard even in public health. However, if one does a proper literature review on the empirical studies, the findings are not so consistent, depending on which greenery data they used, which city they looked at, which health outcome. Maybe most studies do find this what we expect, but there are studies which find either no link or even counterintuitive link. And we wanted to understand from the Earth observation point of view, how should we study this greenery so that actually it will make sense? Why are these studies inconsistent? And so what we have proposed is very simple, actually, very simple. We propose that we should separate spatially where greenery in the urban environment is. And we propose that that we should distinguish between greenery which is found along the roads, we call it on-road, and this is like a 5-meter buffer around main roads. We should distinguish that from the greenery, which is a little bit less accessible. It's off the roads, it's parks, gardens, but anything that I need specially to go to, I need a planned visit to. Whereas our thinking was on-road greenery is the one that I'm going to experience by just going around with my life. Maybe commuting to work, going to the pharmacy, taking kids to school, whatever. So we argued that maybe this greenery is more helpful. Okay, and how we studied it? Of course, we took London because we have lots of data there. There's a very high resolution greenery map for London produced by the city authorities from satellite data. And this is called NDVI, Normalized Difference Vegetation Indices. But then we also collated all the official measures, like the ones in addition to that NDVI, which is very commonly used. There is like WHO measure, which looks also at the proximity of greenery. So for each area, they want to see not only how many parks or how much street greenery there is, but how far it is for the people living there. And then some natural England and so on. So we took these indices, and what you can see already, they are different. It's quite interesting. Depending how you measure, it looks differently. And then we took the ones we proposed. So the left one is on-road, the right one is off-road, the ones we proposed. And then we put these in models to predict health and to see which one of them really matters. Sorry, before that, just a view. So if you have a satellite image to the left, then in the middle, you have the total NDVI, so this full greenery from satellite, and in the right, you see the two we are proposing. And then we use propensity score matching, which is kind of going towards causal with observational data. So let's say it's still associations. And all the official indices, they either have no relationship with our health outcomes or even sometimes counterintuitively they are associated with more prescriptions. And only the on-road greenery consistently in our study gets associated with less prescriptions. And we have tested this at a different level of granularity. So wards, which are bigger areas, LSOAs, which are smaller areas. The result hold. We have also explored like adding walkability, so how many people walk on the roads. The results are also even stronger. And in summary, like if we just look at hypertension, what this shows is that there would be 3.7 fewer prescriptions in areas which have above average greenery, on-road greenery, or if all the areas that are currently below this average would somehow with urban policies be helped to reach that national average, then England or London, in this case, would save £3 million for a year on prescriptions, which is, I think, not unsubstantial. And yeah, that's the work that is still under review, so feel free to challenge us. In summary, using AI and satellite data Earth observation for public health, it empowers to understand more deeply existing knowledge. For example, something about solar radiation that we looked at. It also provides some novel hypotheses, such as this one with the greenery. So we argue that you should look at greenery in a different way. And it can guide policies. So for example, we are now more strongly proponents of ULE's policies because they seem to be supportive of health as well. So that was the second round of projects. And with that, I have covered everything I wanted. I just want to say that this is only a part of the picture. I'm part of a responsible AI team. And the summary is the research that I used to do. But now we are more even like interested in understanding how we should use AI safely, how we should do it responsibly. So I will not talk about it, but there is a lot of work that we put in understanding how also Earth observation or any other data and AI can be used, that they are truly beneficial for us, and it's complicated. So yeah, thank you very much. Happy to welcome any questions.
Thank you very much, Sanja. Do we have any questions?
Thank you. So I was wondering how you deal with the correlation versus causality kind of thing. So, like for example, from the greenery, I can see a reason why you got the results that you got is that while parks might be more beneficial, people need to have free time to go to parks, and so it's a question about economy and the status. So, like I don't know, in general, like in this kind of projects, like how do you make sure that you cover all the variables and that you can say something that has some causal effect and it's not misinterpreted or
No, thank you. It's a great question. And that's why I said it's challenging, because public health experts are a little bit, also close to using these AI methods for the reason that they don't understand them. But I think there are two things. So you ask, how do we make sure we cover as many variables, right? Actually, traditional in public health, they would fit in 4 variables based on theory, right? Where we are here including hundreds. So we are accounting for more. But of course, that doesn't mean that we have causality. I haven't shown, but we do have one work which is going towards causality. We were applying fast causal discovery on MedSet. And the results were also like giving some interesting insights where there is different causal graph, for example, for Asian versus white population and things like that. It's not a finished work. We are collaborating with causal experts to be better. And to be honest, the only way I see this work making impact will be if we collaborate with public health experts, not just us computer scientists coming up with interpretation. And we are working on that, talking to some professors at University of Oxford, Nuffield Healthcare, for example. Thank you.
Thank you. I will start over here.
So thank you for the talk. I wanted to ask if, for example, when you map a city, it might be that the nearby regions have an impact on each other. So, for example, I know that in Frankfurt there is a street which has a ton of drug addicts, and it's pretty much in the financial center. So that would, of course, have an impact. And what do you think about this? Do you think this is something you need to in your experiments take care of, or is it taken care of by some other methods that you use? So what do you think about this?
Can I just make sure I understood the question? So you're talking about the first work I presented, and right, like when we looked at vitality, let's say?
Yes, also yes.
And then your question is how we make sure that our models capture these influences between different... Yeah. No, this is a great question. So actually, the work I presented, I would argue, doesn't capture this, what you're asking. So it's a weakness, except for the fact that satellite imagery is already capturing, like, neighboring areas are similar. So what comes from the data is there. However, we have applied graph neural networks in another work, which I'm not showing here. And I think that could come to the rescue. So with graph neural networks and spatial encoding, you should be able to capture all of these. I think there are, 2 or 3 factors that we think should be considered. One is spatial proximity, and the other is how different areas can influence, because sometimes it's not even only proximity, but maybe if there is not a bridge or not a barrier and so on. So we experimented with that, but that work is under review and I didn't talk about it. But that's a great question.
Thank you. The next question.
It's more practical question. So I see here, so it is exceptional work, and I see immediately a couple of use cases that are far beyond what you have presented here. So really important scientific question. For example, planning of a clinical trials, where to recruit patients, why, and so on and so on. But there is one critical question. So where did you get your data on drug consumption for particular area? Because in this regard, there are huge differences depending on data source.
Absolutely. Thank you for the question. And it's great to hear that you have these ideas. I'd love to think more.
A lot.
So, okay, to your question about prescriptions, I think England is offering a really good test bed. So I do not know how much you know about the system, but in England, we have National Health Services and, right, NHS. And NHS is, as far as I have understood, facilitating even 90% of all the prescriptions. So there are private healthcare providers, but not many people use them. And we got all the data. So we do not have a snapshot, we do not have a partial view, we have all the prescriptions. However, there are many caveats. One is that we had probabilistically to assign them to both conditions and areas. we validated this in some way. I know another issue that we are always acknowledging in our work, maybe white population tend to be prescribed more for the same condition than the, let's say, Asian. There is a little bit of bias there. Yes. Yes, yes, thank you so much. No, absolutely.
Okay, next question.
All right. Thanks so much for the great talk, Sanja. It's a pleasure that you were able to come here and talk to us. I'm sorry I had to miss the second half of your talk. Had some admin stuff to deal with, but I was really interested in the first one. And specifically the study you've done with different Italian cities. And I noticed, for example, that Leave One Out didn't work on Rome, right? So this makes me think, Rome is a bit of a distribution shift compared to all the other cities. So I'm sorry if you already addressed this in the part I didn't see, but would this mean that were you able to train a foundation model on all the urban areas in the world, you would kind of be able to smooth those things out?
Thank you for the amazing question. And first of all, thank you for inviting me. As I said, it's such a pleasure to be back to my home university. Peter, you are already giving a part of an answer. So this study was published, I think, 4 or 5 years ago. I don't think foundational models were yet there. Now we do start to work with that. And to be honest, I think the answer is in that direction. But what I can tell you also from working with the experts in Earth observation domain, generalizability is the biggest problem in general in this field at the moment, because simply the different cultural and physical contexts across the world are quite challenging. But I would love to try foundational models, yes.
Thank you, Sanja, once again. If you have more questions, then you can approach to our chat channel on the Slack. And now I'll move up there.